In this video, we're going to talk about how we model chemical change using something called the balanced chemical equation, ultimately, but we're also going to take a look at how we can use particle pictures to try and visualize what's actually happening at the atomic level. This is sometimes really useful, especially when you're first starting out with modeling chemical change. So what we're going to do is move from words to symbols and then to particles, and then in the process come up with a strategy for how we can create a balanced chemical equation. So this is a word description of a chemical change. When hydrogen gas and chlorine gas react, they form hydrogen chloride gas. Hydrogen is H2. We know that because it's one of the 7 diatomic molecules. To symbolize that it's a gas, after it, in parentheses, we'll put a little symbol G. This is a standard symbol for showing that the state of a substance is a gas. Chlorine is also diatomic, so we'll write Cl2, and it's a gas, so we'll put a G there. Hydrogen chloride, HCl, is also a gas. When we see words that describe a chemical change, like in this case, react to form, we'll model that with an arrow. We don't use an equal sign in chemistry because what comes before and after is equal in some way. The mass is going to be the same, the number and type of atoms is going to be the same, but the arrangement is different. It's very different substances after the chemical change takes place. So we use an arrow instead of an equal sign in our equations. And then there's one more thing. To separate different substances from each other on the same side of the arrow, we're going to use a plus sign. That is what we call a symbolic representation. We're using the symbols and formulae for compounds and elements in this arrangement that looks kind of like an equation. Now let's think about particles. Hydrogen and chlorine both being diatomic would require that we show the particles grouped in twos, and HCl is 1 hydrogen, 1 chlorine, so that's how we would model that. Now clearly we have extra hydrogen and an extra chlorine, so we really are making 2 HCl's. How we show that in the symbol representation is by putting a coefficient of 2 in front. That number written out in front of a formula is called a coefficient. Now, when we've done that, we have created what's called a balanced chemical equation. It's important to note that to balance a chemical equation, you can only do it with coefficients. You can't change the subscripts. Like I couldn't change H2 to H1 or Cl2 to Cl1 to balance this. That's part of the representation of that substance, and you can't change what substance it is by changing a subscript. You can only balance with a coefficient. Let's look at another example. Hydrogen gas and oxygen gas react to form liquid water. So here's the symbolic representation. When we think about it in terms of particles, hydrogen and oxygen are both diatomic. Water has 1 O and 2 H's. We have an extra O here, so that means we're going to need to make another water, but that's going to require 2 more hydrogen atoms, so another hydrogen molecule. We balance the symbolic representation and make it into a balanced equation by putting coefficients of 2 in front of the H2 and the H2O to show that we have 2 particles of each in the reaction. Another one, hydrogen gas, diatomic. Nitrogen gas, also diatomic, reacts to form ammonia, which is NH3. In terms of particles, there's H2, diatomic, another diatomic, N2, and NH3. We can't make an NH3 here because we only have 2 hydrogens, which means we're going to need another hydrogen molecule to provide that 3rd hydrogen atom. But we also have 2 nitrogen atoms, which means we're going to have to end up making 2 NH3s. But that 2nd hydrogen molecule only provided 1 of the hydrogen atoms that we needed to make that 2nd NH3, so that means we need a 3rd hydrogen molecule to provide the other 2 hydrogen atoms to make that 2nd NH3. So we have to put a coefficient of 3 in front of hydrogen and a coefficient of 2 in front of ammonia to make this balance. When we balance these things, we usually don't draw particle pictures, although you can do that if you want to. Most of the time we just take note of how many of each type of atom are on either side and then just make adjustments to make that work out. So for example, the way this is written before we balanced it was that there are two hydrogen atoms, and H2 is two hydrogen atoms, and two nitrogen atoms on the left-hand side of the arrow. On the right-hand side of the arrow, we have three hydrogens and one nitrogen. Now we want to think about how can we make coefficients balance this. 2 and 3, the least common multiple of that is 6. So if we put a 2 in front of the NH3, that gives us 6 hydrogens, and a 3 in front of H2, that gives us 6 hydrogens. So that balances the hydrogen. Now we've got 6 and 6. The other thing that it did was it gave us 2 nitrogens, and so now that balanced the nitrogen. Here's another equation to balance. On the left-hand side, we have 1 aluminum and 2 oxygens. On the right-hand side, we have 2 aluminums and 3 oxygens. Once again, we have that least common multiple of 6 thing with the oxygens. If we put a 2 here and a 3 here, we will have 6 O's on both sides, so that balances O. But when we put that 2 in front of Al2O3, that changed aluminum to a 4. So to balance that, we would need to put a coefficient of 4 in front of the aluminum, and now we have a balanced chemical equation. There are 3 types of chemical equations, 3 ways that we represent these things. The first type is called a molecular equation. A molecular equation shows a complete ionic or molecular formula for all reactants and products. When we talk about a chemical equation and we don't mention any of the other types, this is sort of the default. This is what we're talking about is a molecular equation. So the equations that we've had so far in this video, those have all been molecular equations. There's another type of equation called an ionic equation. Ionic equations show electrolytes that are in solution as dissociated or ionized ions. What counts as an electrolyte? Soluble ionic compounds, things that are ionic compounds that dissolve in water readily, will break up into cation and anion that are loose in water. And so that makes them able to carry electrical current. The other thing that's an electrolyte is a strong acid. Strong acids react with water, and by reacting with water, they make hydronium ion and some anion. The hydronium is a H3O+. And so those things will be written as dissociated or ionized ions. So in an ionic equation, the things that can split up are shown as split up, as ions. And then the third type of equation is called a net ionic equation. In an overall complete ionic equation, you're going to have some ions that it becomes clear are not undergoing chemical change. They're the same on the left-hand side and the right-hand side of the arrow. These are what we call spectator ions. In a sense, they are just there to watch what's going on with the active ions. A net ionic equation removes the spectator ions and only shows the species that are undergoing change. In order to be able to create ionic equations, we need to know which are the ionic compounds that dissolve and which don't. So we're going to go over some solubility trends. Here's a list of things that are usually very soluble. So you can think about these as things that you can split up in an ionic equation. Group 1 compounds, that's the first column. Lithium, sodium, potassium, rubidium, cesium, francium. If those are the cation, it's probably going to dissolve in water very well. NO3 compounds, this is the nitrate ion. If the nitrate ion is the anion, it's usually going to be in a compound that's very soluble. SO4 which is the sulfate ion. These things are usually very soluble. There are 3 exceptions: calcium, strontium, and barium. If those are the cations, then that compound is not going to dissolve very well. But otherwise, compounds in which sulfate is the anion are going to be very good at dissolving. It's a little bit easier to remember these 3 if you recognize that they're all in column 2. It's a little bit harder to remember them because not all column 2s have this insolubility with sulfate. What are called the lower halides, chlorine, bromine, and iodine ions, these things are usually very soluble, but there are 2 exceptions. If silver is the cation or if lead-2 is the cation, then they are not going to dissolve very well in water. And ammonium compounds. This polyatomic cation, NH4 1+, is called the ammonium ion. If it's the cation, then probably what you have is very soluble. Now let's look at some things that are usually very insoluble. So these things don't dissolve well in water, which means you shouldn't show them as broken up into ions in an ionic equation. Hydroxide compounds. If hydroxide, the OH1- ion, is your anion, these things are probably not going to dissolve in water. The exception, calcium, strontium, and barium. Those are the same things that made sulfate insoluble. These things make hydroxide soluble. Sulfide compounds, that's the S2- ion. These things are usually not soluble, but with that same three exceptions. Calcium, strontium, and barium sulfide do dissolve, okay. Carbonate compounds, usually very insoluble. Now, if the cation is a group 1 or ammonium, then of course that's exceptions to all of these, because those things, no matter what the anion is, are usually going to be soluble. Okay, let's put this into practice with a couple of examples, and we're going to give all three equation types. So let's start out with the molecular equation for this reaction. Aqueous lead-2 nitrate. So lead-2 nitrate is going to be Pb, that's a 2+, nitrate is a 1-, so we're going to need 2 nitrates to balance that lead-2. It's aqueous, that means dissolved in water. The little symbol that we use for that is an AQ. And aqueous potassium iodide. So potassium iodide is K, which is 1+, iodide is 1-, so it's a 1-to-1. Aqueous symbol. React to form, there's my arrow. Solid lead-2 iodide. So lead-2 is a 2+, iodide is a 1-, so we need a 2 subscript on the iodine because we need 2 iodines to balance the 2+ charge of lead. And this is solid, so we're going to use a little S symbol for that. And then aqueous potassium nitrate. So potassium is 1+, nitrate is 1-. We only need 1 of each, and this is aqueous. It's not balanced because we have 2 nitrates on the left and only 1 on the right. So if we put a 2 in front of potassium nitrate, that balances the nitrate. That means we have 2 potassiums, though, so we need to put a 2 in front of potassium iodide to balance potassium. And that gives us 2 iodides, which is fine because we have 2 iodines in the right-hand side as well. Okay, now, that's the molecular. Now let's do the ionic. In this case, we're going to split up everything that can be split up. The aqueous species are the things that dissolve. Nitrates are all soluble, so we can split up Pb2+ and NO3 1-, but there's 2 of them. We can also split up potassium iodide. That's going to give us 2 K+ and 2 I-. And we're putting the 2 there because there's 2 Ki's. On the other hand side of the arrow, PbI2 we cannot split up because iodide is a lower halide, and with lead-2 it's not going to be soluble. So we have to keep this together as PbI2. Potassium nitrate does split up because it's soluble, so that's going to give us 2 K+ and 2 NO3-. So this is the ionic or complete ionic equation. The last equation that we want to give is the net ionic equation. So to do the net ionic equation, we have to locate the spectators. The spectators are things that aren't actually undergoing any change. We have K+ on the left-hand side and also on the right-hand side. There's no change there. NO3 on the left-hand side, there's also NO3 on the right-hand side. No change. The only real change that's happening here is that the lead and iodide ions don't exist separately after the change takes place. So that's all we're going to include in this net ionic equation. So there's our net ionic equation. Let's do another one. Aqueous hydrochloric acid. Hydrochloric acid is HCl. It's aqueous. And aqueous sodium hydroxide. Sodium is a 1+. hydroxide, OH, is a 1 minus, so it's 1 to 1. React to form, there's our arrow, water, H2O. Now, water, unless we have other information about it, we assume that it's a liquid, and so the little L symbol that we would normally put down for liquid, that's optional. I'll put it in here, but we don't have to do that. If we don't put a phase symbol for water, it's assumed that it's liquid. And aqueous sodium chloride. So sodium is a 1 plus, chloride's a 1 minus, 1 to 1, so that's aqueous. There's the molecular equation. Now let's split up what we can split up. Hydrochloric acid is one of our 6 strong acids. So we're going to show this as H plus and Cl minus. Sodium hydroxide is aqueous. It's split upable. Na plus, OH minus. On the right-hand side, we have water. Water is a molecule. It's not an ionic compound at all. The only molecules that can be shown split up in an ionic equation are strong acids, which water is not. So we got to keep that together as H2O. NaCl, that's an ionic compound that's soluble. So that's Na plus Cl minus. So there's our complete ionic equation. Now let's locate our spectators. Sodium ion is not undergoing any changes. Chloride ion is also not undergoing any changes. The only real change that's happening here is that the H plus ions and the OH minus ions are getting together to make water. So that's our net ionic equation for this reaction.